Section 2.1 is entitled The Derivative at a Point, and here we're going to introduce the derivative function, which is really one of the most important topics from Calculus 1. So let's do a brief recap of what we've been discussing in class. But lately we've been letting s of t denote a displacement function. It might represent, if I'm traveling somewhere, the distance at a particular point. And then we fix a particular instant in time, and usually I've been denoting a as that time. And then we fix a small time increment, which we usually call h. The average velocity between the starting time t equals 8 and a little bit later, which is t equals a plus h, is s of a plus h minus s of a divided by h. This is a change in distance divided by a change in time, or a change in displacement divided by a change in time. H represents time. This also equals the slope of the secant line connecting t equals a and t equals a plus h. So this quantity has two meanings. The formula, it's an average velocity between 2 points in time, and it's the slope of a secant line connecting 2 points on the graph. An example that we've recently been discussing is something like s of t equals minus 4.9 t squared plus 20t. This describes the height above the ground of an object if I've thrown it vertically. Let's say I want to look at the average velocities between t equals 1 and t equals 1 plus h for smaller increments of h. In this case, I'm going to look at a equals 1, so I'm interested in average velocities starting at 1. What I've done in this picture is I've graphed the parabola. So at time 0, we see the object is 0 meters above the ground. Units are meters and seconds here. And at about 2 seconds, the object reaches its maximum height here. So s of 1. If I use the formula for s, which is right here, and plug 1 in, I get 15.13. Let's take a value of h, which is 1. Then 1 plus h is 2. If I take 1 plus h and plug it into the formula s, I get about 20.4. And again, I use the formula for s on the previous page. Now take a look at the graph. This point A that I've labeled is 1 comma 15.13, or in other words, 1 comma s of 1. The point B that I've labeled here is the 2 comma 20.4. In other words, it is 1 plus h, s of 1 plus h. Now, 1 and 1 plus h are horizontally h units apart. 15.13, which is s of 1, is this height right here. If I subtract that from 20.4, which is s of 1 plus h, I get this little height right here. So this horizontal distance is h, and this vertical distance is s of 1 plus h minus s of 1. So that means the slope of the secant line connecting these 2 points is s of 1 plus h minus s of 1 divided by h. And that is 20.4 minus 15.13, which works out to be 15.27, about 5.27 meters per second. Now we're going to look at a smaller value of h. We can see from the graph that if I use a smaller value of h, the point B is going to move closer to the point A, and I'm going to have a secant line whose slope is larger than the one we just computed, which is 5.27. So we're going to go to a very small value of h, 0.1. In this case, 1 and s of 1 remain the same, 1, 15.13. h is 0.1. That's a time increment of 0.1 seconds, so 1 plus h is going to be 1.1. In this case, if I take 1.1 and plug it into s using the formula, I get 16.07. So 1 plus h, comma, s of 1 plus h is 1.1, comma, 16.07. Now I have a triangle just like the one I had on the previous page, but it's a very, very small triangle. The length of the base is 0.1. The height is s of 1 plus h minus s of 1, just like on the previous page, but in this case, 1 plus h is 1.1. So the numerator is s of 1.1 minus s of 1, and that's going to be a small difference. But we're dividing by h, which is small as well. If we take these quantities, 16.07, and subtract 15.13, and divide it by 0.1, we get about 9.4 meters per second. All of these are slopes of secant lines. All of these are average velocities. And we know from discussions in class that as h becomes closer to 0, our average velocities approach the instantaneous velocity. As the time increment h becomes smaller, without equaling 0, the average velocities, s of a plus h minus s of a over h, become closer to the instantaneous velocity at time t equals a. And we write that using limit notation, the limit as h goes to 0, s of a plus h minus s of a divided by h. So this quantity represents, this limit represents the instantaneous velocity at a particular point in time, and it is the slope of the curve, in other words, the slope of the tangent line at time a. Let's take a look at a particular example, the one we had before. The instantaneous velocity at time 1 second. H equals 0, the limit is h equals 0, s of 1 plus h minus s of 1 divided by h. Here we have expressed the instantaneous velocity, or the slope of the tangent line, as a limit. Now I'm going to do some little side calculations, which I'm going to denote right here. I'm going to evaluate s of 1 using the formula, which was 15.1. I believe that's the same thing we saw a couple pages ago. In this case, s of 1 plus h. I'm not going to use a particular value of h. I'm just going to use h in general. So what I do, I go to my formula for s, and everywhere I see the input t, I replace t with the quantity t plus h. What we're using here is composition of functions, and we need to be very careful. Sometimes it helps to just put a little box here around t to remind yourself that what you're going to put in the box is t plus h. So we're going to take minus 4.9, and then we're going to take t plus h quantity and square it. We're going to plug t plus h into this box, so we'll have 20 times t plus h, or in this case, 1 plus h. We're substituting 1 plus h in everywhere we see a t. Okay, so let's expand this. 1 plus h quantity squared is 1 plus 2h plus h squared plus 20 times the quantity 1 plus h. Be careful about including parentheses. Otherwise, instead of getting 20 plus 20h, we might just accidentally write down 20 plus h. Let's take the minus 4.9 and multiply it by each of these three terms, and we get minus 4.9 minus 2 times 4.9, which is minus 9.h, minus 4.9h squared plus 20 plus 20h. Now these were my little side calculations. What I'm going to do at this point is I'm going to take the simplified version of s of 1 plus h, substituted in here. I'm going to take s of 1, substituted in here. I'm going to simplify, divide by h, and let h go to 0. So here is s of 1 plus h, which I have substituted in here, and then I subtract s of 1. That's a 15.1. Now I'm going to do a little bit of algebra here. If I take minus 4.9 and minus 15.1, add them together, I get minus 20. That minus 20 is going to cancel with that 20. So these three guys together cancel. Now, if I have 20h and I subtract if I subtract 9.8h, in other words 20h plus negative 9.8h, that gives me 10.2h. And then I'm going to subtract the minus 4.9h squared. That's an h. And then I'm divide by h. Now we're ready to factor in h out of the numerator. So we have the limit as h goes to 0. H times 10.2 minus, I'm running out of space here, 4.9h, sorry about that, divided by h. The h's cancel because h is not equal to 0, it's close to 0, and if I plug 0 in for h here at this stage, I get 10.2 minus 0. This is 4.9h. If I plug 0 in for h, I get 0. So this is 10.2 meters per second. That is the exact velocity. By using the limit, we actually computed the exact velocity at time 1 second. That kind of makes sense because if I draw a tangent line, these 2 points were close together, but if I actually draw a tangent line, it's going to have a slightly larger slope than the secant line whose slope was 9.4. So a value of 10.2 is not surprising. Now we've been doing all of this in the context of velocity, but we can do this in general for any function. Let me zoom in just a little bit here. I'm going to be giving you this handout in class. This is introducing what we call the derivative. So let's suppose that we have some function. Perhaps it has nothing to do with velocity. It might arise in some other context. We draw a graph of the function. I've drawn a parabola in this case, and we fix a point a comma f of a. We want to be able to determine the slope of the curve or the slope of the tangent line at this point. We move a little bit to the right, h units. So now we take this x value, which is a. The new x value is a plus h. If we take a plus h and plug it into f, we get f of the quantity a plus h. Just like a few slides ago where we saw computed this difference, in this case it's this height, which is f of a plus h, minus that height, which is f of a. So that's the height of this little triangle here. The slope of the secant line, therefore, would be f of a plus h minus f of a, all divided by h. So here's that quantity again. That is the slope of the secant line. I'm going to zoom in just a little bit more. Connecting the points a, f of a plus h, f of a plus h. In terms of its physical or contextual meaning, it is the average rate of change of f with respect to x over this interval from a to a plus h. If our context was velocity, it would be an average velocity. Now we let h become closer and closer to 0 without actually equaling 0. The secant line slopes become progressively closer to the tangent line slope, and the average rates of change become progressively closer to what we call the instantaneous rate of change. And we call the resulting quantity the derivative of the function at x equals a. And we denote that by f, and then there's a little superscript prime of a. So going back to the previous example. Here's my parabola. Here's a, f of a. F prime of a is the slope of the tangent line to the graph at x equals a. Or another way to say that is it's the slope of the curve at this particular point. In this case, the slope of this tangent line or the slope of the curve at this point is positive, so we would expect f prime of a to be positive. In English, f prime of a is the limit as h goes to 0, f of a plus h minus f of a divided by h. In terms of slope, it is the slope of the tangent line to f at a particular point, a, f of a, not between 2 points. In terms of its meaning, it is the instantaneous rate of change, or the average rate of change of the function f with respect to x at x equals a. In the diagram above, f prime of a is positive since this function is increasing at this point. Now, we've been talking mainly about displacement and velocity, but when we talk about other contexts, f might represent the pressure of a gas, or it might represent the amount of drug in a person's bloodstream. This instantaneous rate of change is going to have a different meaning. Let's take a look at a simple example. I'm going to look at f of x equals 2x squared plus 1. And I'm going to calculate f prime of 2. This is the slope of the tangent line at x equals 2, which we can see from the graph is going to be positive. First, we're going to write it as a limit. The limit as h goes to 0, f of 2 plus h minus f of 2 divided by h. That's f prime of 2 written as a limit. It has an interpretation with regard to slope. It is the slope of the function, 2x squared plus 1 at x equals 2. Or in other words, the slope of the tangent line, not secant line, at x equals 2. It is a rate of change. It is the instantaneous rate of change of the function at x equals 2. Now we can compute this quantity algebraically, just like we did for the last example, the distance displacement. F of x equals 2x squared plus 1, f prime of 2, expressed as a limit. Here I'm going to do my little side calculation. I'm going to plug 2 into f. I get 2 times 2 squared plus 1, which is 9. I'm going to take the formula for f, and I'm going to evaluate it at 2 plus h. In other words, wherever I see an x in my formula, I'm going to replace x with 2 plus h. I'm going to expand this quantity. 4 plus 2h plus h squared. 4 plus 4h plus h squared. I'm going to multiply that by 2 and add 1. It simplifies to be 9 plus 8h plus 2h squared. So I've done my little side calculation. F of 2 plus h is this quantity. I'm going to subtract f of 2, and here's what I get. The 9's cancel. We can factor in h out of 8h plus 2h squared. We can cancel the h's because h is not equal to 0, as guaranteed by this notation. Now we have the limit as h goes to 0 of 8 plus 2h, and as h gets closer to 0, this gets closer to 0, so we can simply plug in 0 for h, and we get 8. So that means the slope of the tangent line to the function 2x squared plus 1 at 2, f prime of 2, the slope of that tangent line is exactly 8. So I'm going to give you a couple problems to work on. For each problem, I want you to write f prime of 1 as a limit. Remember, this is how we express the derivative as a limit. So you're going to want to replace the 2, obviously. Interpret f prime of 1 in terms of slope. Be very careful. Is it a tangent line or is it a secant line slope? Interpret in terms of rate of change. Be careful to distinguish instantaneous versus average rate of change, and then calculate the limit from 1. In other words, calculate f prime of 1. Here are two functions. F of x equals x squared plus 2x minus 5. So do all of this analysis, 1 through 4, for this function, and do the same thing for f of x equals x to the third plus 4. Now, just a word of warning, I know some of you have taken some calculus before. You will probably want to use a shortcut. I won't explain what that shortcut is to calculate f prime of 1, but that's not what I want you to do here. No shortcuts yet. You actually have to evaluate the limit using this process that we just went through. I'll see you in class then.